Hello, everyone. Okay, so we are in module 5, and I want to just say something about what we were doing on Tuesday. I had a question in office hours. And so the question was, when you did the numerical integration, you already knew what the chart was going to look like. So how are we supposed to know what our chart looks like? So I said, oh, that's a great question to handle in class because you're probably not the only one who had that question. So I just want to look at this problem here using Euler's method with h equal to 0.5, find y of 3 if dy dx is equal to x times y. Okay, so, and they give you y at 1 equals 1. I think I'm going to change that to y at 1 equals 2. There we go. All right, just to make it a little bit different. Okay, so in this problem, can anybody tell me what x naught and y naught are? That's where we're starting. So remember, we're using the numerical method to go point by point by point by point to graph the solution to the differential equation. Okay, so I need x naught, I need y naught, and I also need to know what is f of xy. So any takers on any of those answers? Wow. Are we really this lost? Okay, so let's go back to the original problem. And the original problem was here. dy dx is equal to f of xy, and y of x naught equals y naught. Okay, that's what we did on Tuesday. All right, so now does that help? Can anybody tell me what x naught, y naught, and f of xy is? Devin, what's x naught?
I'm not sure.
Okay, so x naught is, so again, this is what let me go back. This time I'm going to snatch it. Okay, so now look at the form of the problem. What is f of xy?
Dy over dx.
Okay, and that is in this problem, what is it equal to?
Xy.
Good, thank you. All right, so what's x naught? X naught is what's in the parentheses. 1. Y naught is what it equals. 2. Okay, so that's the beginning of the problem. All right, and we're going to use Euler's method in order to solve this. So if we know that we're starting at x naught equals 0 and we want to go to x equal to 3, we're trying to approximate y of 3, then we have an interval that looks like this from 1 to 3. And we're doing increments of a half. So that means we'll get to 1.5, that's there. We'll get to 2. We'll get to 2.5. and then we'll get to 3. So that says to me, I need to do 4 iterates. Another way to find it is if you remember from our other rules, H was equal to B minus A over N. Just solve for N. N is going to equal B minus A over H. So B minus A is 3 minus 1, which is 3 minus 1, and H is a half. So I get 2 over a half. So that's 4. So as you can see, we have to do 1, 2, 3, 4 iterates to get up to y is equal to 3. Okay, so now I can draw my chart. All right, this is n, this is x, and this is y. We have n equals 0, n equals 1, n equals 2, n equals 3. We know we need to do 4. X naught was 1. This is 1.5. I know this is going to be 2. This is 2.5, and I know this is going to be 3, and y naught was equal to 2. Okay, so we're starting there. All right, so our formula was yn equaled yn minus 1 plus h times f of xn minus 1.
I'm sorry, really quick, could you scroll back up?
I certainly can. What do you want? What do you want to see?
Like up until you made the, right there is good, right there.
No problem.
All right, thank you.
You're welcome. Okay, do you see how I'm making my chart, Devin?
Yeah.
Okay. All right, so now what I'm trying to get to is, I know y of 1. I need y of 1.5, and then I'll get y of 2. Then I'll get y of 2.5, and then I'll get y of 3. And then I will have satisfied the problem, which is to find y of 3. Okay. So we have yn is equal to yn minus 1 plus h, and f of xn minus 1, yn minus 1 says n minus 1 times yn minus 1. Oh, this one has a nice little formula. I can do yn is equal to, I can factor out yn minus 1 and multiply it by 1 plus h times xn minus 1. So that's how I'm going to find each of the y's. I'm going to use this formula to find each of my y's. Okay, so I start off with x naught or x0 was 1 and y0 or y naught is 2. I think that's what we had, 1 and 2, yes. Okay, so x1 is 1.5. We already did that. We figured that out on the table. So therefore, y1 is going to be y naught times 1 plus h times x naught. All right, well, that's not hard. So that is going to be y naught, which was 2. So y naught was 2 times 1 plus h was 0.5 times x naught, which is 1. So that is 3. Okay, so y1 is 3. All right, let's find y2. So we know x2 is 2. So y2 is going to be y1 times 1 plus h times x1. And that is equal to y1 was 3 times 1 plus 0.5 times x1 is 1.5. 5.25. So now we know y2. y2 is 5.25. And then you continue to find y3 and y4. I'm sorry. Yeah, y3 and y4. And when you get to y4, that will be your approximation for y at 3. Okay, any questions? So that is what we worked on Thursday, and how you create your chart. Your chart is based on the number of iterations you need to make to get to whatever they asked you to do. All right, any questions? All right, hearing none, we will move on to our section for today. And our section for today is separable differential equations. Our objectives, we're going to use the technique of separation of variables to solve differential equations, and we're going to solve some applications using the separation of variables technique. So I grabbed the definition from Tuesday. An ordinary differential equation is an equation containing an independent variable x or t and a combination of a dependent variable y and its derivatives. So we're looking at first order differential equations. So therefore our derivatives are only one. So we have dy dx, which is a first derivative. That's what we have. And that is equal to some function of xy. We need to solve for what y. And they may or may not give you an initial condition. If they do, you have to solve for all constants. Okay, so this technique, which is separable ordinary differential equation. So this technique that we're going to use, separable ordinary differential equation, we are able to split this function f of xy into two distinct functions, one that only has x's and one that only has y's. It may look like the product of two functions. So you may have f of x times g of y, or you may have a rational function, f of x on the top, g of y on the bottom, or g of y on the top, f of x on the bottom. Okay, so for example, f of xy equal to x squared, y squared is separable. Okay, f of x is just the x squared part, and g of y is just the y squared part. Okay. So some things are not separable. You will not have those problems to do, but I just want to show you what I mean by not separable. So f of xy equal to the cosine of xy is not separable. So I cannot split it. Okay, so we are going to use the theory of differentials. And in the theory of differentials, we're going to split this differential equation based on dy and dx, and then solve for the y function and solve for the x function. Okay, so what do I mean by that? Here's my first example. So I have dy dx is equal to y. Okay, so I'm going to do dy is equal to y dx, and then I'm going to get dy over y is just equal to dx. Okay, so now I have y's on one side, x's on the other. Then I need to integrate. So when I go to integrate, I'm going to integrate dy over y. And I'm going to integrate dx. Okay, what's the integral on the left-hand side? What's the integral of dy over y? This is one we see over and over and over again. Dy over y, dx over x, du over u. What do they all give you?
Natural log of y, of the absolute value of y.
Good, the natural log of the absolute value of y, and I get a
Plus c.
constant. Mhm. And on the other side, I just get x plus a different constant. Now, this is where I'm only going to do this one time. And then after this, you'll see that I don't need to do it again. I can make this the natural log of y, absolute value of y, is equal to x plus c2 minus c1. But c2 minus c1, that's just a constant. So I'm going to replace it with one constant c. So notice you only need to put your constant c on one side. Okay, so now I'm still trying to solve for y. So I'm going to take e to the natural log of the absolute value of y. And then I'm going to get e to the x plus c. Now on the left-hand side, I'm just going to get the absolute value of y. And on the right-hand side, I'm going to get e to the x times e to the c. But here we notice e to, big mistake. That's e to the c. And here we notice that we have this e to the c. I'm just going to call that a because that's e raised to a constant. So I get the absolute value of y is equal to a e to the x. Okay. So this function, I'm going to drop the absolute value because if a is negative, it will make y negative. And if a is positive, it will make y positive. So we're going to get y is equal to a e to the x. And this is the general solution of the ODE. So that's the general solution. And the general solution will contain constants that we don't know what they are. Okay, now for this particular problem, they gave you, or I gave you, what we call an initial condition, where I told you that when x is equal to log 2, y is 4. All right, so since we are given that y of the natural log of 2 is equal to 4, we must solve for all constants. All righty. So to solve for the constants, I said if x is equal to the natural log of 2, then y is 4. So let's plug it in. So we get 4 is equal to a e to the natural log of 2. Can I simplify that? Can I simplify e to the log of 2? What does that simplify to become? We learned this way back when we were learning about exponentials and logs being inverse functions of each other.
Is it just 2?
It is just 2. Thank you. So you get 4 is equal to a. Remember, e and log are going to, they're inverse functions. So you just get times 2. So you get a is equal to 2. So now I have y is equal to 2e to the x. And this happens to be the unique solution of the ODE that corresponds to the initial condition. Okay, any questions? Okay. Our next problem. There it is. Okay, so this is our next problem. All right, so can somebody tell me what f of x is and what is g of y?
F of x is e to the x and
Okay,
g of y
and g of
is
y,
1 plus y.
excellent. Okay, so the g of y is what's going to have to move. All right, so we're going to multiply by the dx. So we're going to get dy over our 1 plus y is going to be e to the x times dx. Any questions? Okay, we now want to integrate that over 1 plus y is equal to the integral of e to the x dx. So what's the integral on the left-hand side? It's just a linear term. We've seen terms like this in partial fractions. We can integrate it. It's just a natural log of the absolute value of 1 plus y. On the right-hand side, I'm going to integrate it so I get e to the x plus a constant. So this is the general solution. Okay. Now, again, they gave us some initial information. Y of 0 is 0. So we need to find the specific. So since y of 0 is equal to 0, we're going to get the log of 1 plus 0 is equal to e to the 0 plus a constant. So I plugged in x is equal to 0 and y is equal to 0. And in doing that, I get the log of 1 on this side is equal to 1 plus c. I know the log of 1 is 0, so I get 0 is equal to 1 plus c. So now I know my constant has got to be -1. So now I get the natural log of 1 plus y. And I think they told me, oh, nope, they didn't tell me anything. So that's all I get. I'm thinking of the next problem. Of 1 plus y that's going to equal, okay, e to the x. And then we solve for the constant, it was -1. So this is our specific solution. All right. And this solution happens to be, this is a unique solution, but it happens to be an implicit form of y. So this is the unique solution in an implicit form of y. Okay. Questions? All righty. Here is example 3. Okay, we need to identify x, f of x and g of y. And then what's f of x?
Is it 2x?
2x. And g of y?
Is the square root of 1 minus y squared?
Okay, awesome. All righty, so let's move it. So I want all y's on this side. So I get dy over the square root of 1 minus y squared. And that's going to equal 2x dx. All right. All right, integrate both sides. Somebody want to give me the integral of the left-hand side.
Is the natural log of the square root of 1 minus y squared.
Okay, it would be if there was a y in the denominator. Nope, it still wouldn't be. Because it is the square root of 1 minus y, it is that value raised to the -1/2. And so we can't get a logarithm out of that particular expression. But it is a special function. Can anybody recognize what it is? We've done a lot of these.
Sine inverse.
Okay.
Sine.
All righty. So I'm going to get on this side the sine inverse. It is y over 1, so that's just the sine inverse of y. And this side is going to give me x squared plus a constant. Okay. I can take the sine of both sides and I get the sine of the sine inverse of y is equal to sine of x squared plus c. So that says that y is equal to the sine of x squared plus c. Okay. Now, we have some information. So our information is y at 0 is equal to 1 over the root of 2.
Oh, babe. See you. You were just about to leave me.
Okay. So y of 0, 1 over the square root of 2. Now, that says 1 over the square root of 2 is equal to the sine of x squared, that's 0 plus c. So I get 1 over the square root of 2 is equal to the sine of c. Now, I really only want one answer, and it looks like I could have a bunch of answers. C could be pi over 4.
What? What's due tonight? Next week?
The sine of pi over c could be pi over 4, because the sine of pi over 4 is 1 over the root of 2. C could be 3 pi over 4, because the sine of that is 1 over the root of 2. So this question looks like it doesn't have a unique solution. And in some ways, there's some theory behind it that it may not, but let's go back and look at this equation right here. And this is going to be the equation that's going to help us out. All right, it says the sine inverse of y. So if we use the sine inverse of y is equal to, put in sine inverse of y is equal to x squared plus c. Then we get the sine inverse of 1 over the root of 2 is equal to 0 plus c. Okay. So c is the sine inverse of 1 over the root of 2. Now here's where we can limit it, because we know sine inverse only goes between minus pi over 2 and pi over 2. So therefore, c has to be pi over 4. So c has to be pi over 4, since negative pi over 2 is less than or equal to the sine inverse of theta is less than or equal to pi over 2. Okay. All righty, so now we have an answer. If I can go back and find it, y is equal to the sine of x squared plus pi over 4. And not only is this a unique solution to the problem here, it is also explicit. I got y equals, so I can see everything. Okay, this next one,
Can you scroll back up?
I certainly can. Let me plop this in and I will scroll back up. Where do you need me to go? Rodney? Is that good?
Yeah, that's good. I'm sorry. I didn't know my mic wasn't on.
Okay. All right, so this next problem is not in the form that we've been looking at. This next one looks like, wow, what do I do with that? Okay, so let's go through it. So we have y times x plus 1. And then y prime, I'm now going to write it as dy dx so I can see the differentials is x times y squared plus 1. Okay, so I am going to take roll while you guys put that in the right form. Okay, I am back from taking the roll. Can somebody tell me what their equation looks like? putting all the y's on one side and all the x's on the other, what does your equation look like? Okay, guys, you had ample time to be able to get this done. I didn't say solve the whole problem. I just said do the separation. Anybody? Aaron, what does your separated problem look like? Aaron. Okay, Johnny, what does your separated problem look like? Okay, now I need to check to see if my mic is working. It is it? Is it? Can y'all hear me?
Yeah,
I can hear you.
Yeah.
Okay, then can somebody answer my question? Wow. Wow. This is algebra. Okay, I have y, x plus 1 dy is equal to x times y squared plus 1 dx. Then I'm going to move everything that's an x, everything that's a y moves to the left.
oh, that's all we're doing.
So I get y over y squared plus 1 dy, and everything that's an x
Oh,
over.
that was simple.
I know, it was simple. Thank you for recognizing it.
You're welcome.
Okay. How do you feel?
Great.
That went hard. Okay. Now comes the harder part. The hard part comes when we integrate it. Okay. Now we're going to put an integral in front of it. All right. So when I did this problem, I did it by doing the left hand first and then doing the right hand. So let's do the left hand side. So left hand side is the integral of y over y squared plus 1 dy. Okay, so anybody have an idea of how we're going to integrate this? This is a way back problem. Okay, this is way back and it's not a difficult one. Anybody know where to start? Okay, I'll give you a hint. Use substitution.
I was just,
Does that help?
yeah.
Okay, then tell
So-
me how it helps.
Oh, wait. Is you gonna be y? Wait, no. No, it's not. It's not gonna be y.
Remember, u is always the difficult part.
Yeah.
So what's u gonna be?
It's gonna be y squared plus 1.
Absolutely.
Oh,
Okay,
wait, and then du is gonna be 2y dy.
good. And keep going.
And then dy is gonna be du over 2y.
Okay, we don't want, well, okay, some people do it like that. I always keep the variables together. So I would keep du over 2. And I would make this y dy. And since I have y dy in the problem, I can substitute it straight.
Okay, that makes sense.
Okay, good. All right, so now we're ready. This is the integral. Y dy is du over 2. And then y squared plus 1 is just u. So this is 1/2 the integral of du over u. And what is that?
ln u
Okay,
over u.
1/2 the natural log of the absolute value of u plus a constant. So that's 1/2 the natural log. Since u is y squared plus 1, which is always positive, I can get rid of the absolute value. And I get plus c. So that's the left-hand side. Okay. Thank you, Rodney.
Cool.
Real good, real good. Okay, let's do the right-hand side. Right-hand side is the integral of x over x plus 1. Now, we just did this one, okay? This was a problem where we had to integrate a rational function and the power of the numerator and the denominator are the same. So what did we do for that problem? Or we could use u substitution for this problem.
So we can do the same thing.
Well, the u substitution is going to be a little different. So if you, what would you let u be? Again, use the most difficult part of the problem, right?
Yeah, x plus 1.
Okay, so let u be x plus 1. Okay, so that takes care of this. What's du?
It's just gonna be 1
Dx.
dx. Yeah.
Good. So that takes care of this. Now what do I do with that x? Give you a hint.
Wait, is it gonna?
What can I do with that x? I can make x equal to what?
X.
U over 1?
Not u over 1, u minus 1.
Oh, yeah, yeah.
Okay,
Wait, why is it u minus 1?
because I have u is equal to x plus 1.
Right.
So if I subtract 1 from both sides, I get x.
Okay. Okay.
All right. So this is the integral. In the place of x, I get u minus 1 divided by u du. And we would have gotten the same thing if we had done long division. This is the integral of u over u is 1 minus 1 over u du. So that's u minus the natural log of the absolute value of u plus a constant. So u is x plus 1 minus the log of the absolute value of x plus 1 plus a constant. And we're going to take that 1 and throw it in with the constant. and get x minus the log of the absolute value of x plus 1. And we get a different constant, call it C2, I don't care. Okay, because remember, all of our constants going one place. All right. So that's the right-hand side. Okay, so now we're going to take, and our integral on the left-hand side gave us 1/2 the log of y squared plus 1. And the integral of our right-hand side gave us x minus the natural log of the absolute value of x plus 1. And then we put all our constants together as one constant, and we get that. And so we get a general solution to the problem that looks like that. Okay, any questions? Any questions?
What was the other method if we didn't use substitution? If we could run by that.
Okay, the other method was long division. Thank you for asking. Okay, so we could have the integral of x over x plus 1 dx. We could have used long division. So we would have taken x plus 1 and divided it into x. So you get x goes into x one time. 1 times x plus 1 is x plus 1. Then you subtract, x minus x gives you nothing, and 0 minus 1 gives you -1. So that's the remainder. So therefore, you get x plus 1, x over x plus 1 is actually equal to 1 minus 1 over x plus 1. So it factors like that. So then when you do the integral of x over x plus 1 dx, you're just integrating 1 minus 1 over x plus 1 dx, and that again still gives you x minus the natural log of the absolute value of x plus 1 plus a constant. So this is using long division. Okay. All righty. So I want to say some things look separable that aren't, and some things that aren't separable look like they are. So let's take, for example, the integral, I'm sorry, dy dx. I think I gave you this one. Well, no, e to the x plus y. So that is separable. So f of x, y equal to e to the x plus y simply becomes e to the x times e to the y because of the way powers work. So therefore it is separable. We got one function of x times another function of y. Okay, so you can get dy dx is e to the x times e to the y. And so if I multiply by x and divide by e to the y, I get e to the -y dy is equal to e to the x dx. And so I can integrate both sides and I get negative e to the negative y is equal to e to the x plus a constant. And so that could be written as e to the x plus e to the minus y is equal to a constant. And so that would be the solution to that differential equation. So it doesn't look separable, but it is. So be careful of exponentials that are products, like where the power is a product, because it could be separable. Okay, any questions? Okay. We're going to do an application. Okay, so there are two applications that we're going to do. There are many applications. Your text covers some. I'm going to cover two. The first one is going to be radioactivity. Okay, so when atoms are unstable, they spontaneously emit radiation by a process called radioactive decay. And so you may have radioactive material and it will decay over time. The rate of decay is proportional to the amount of radioactive nuclei present. So this is a big deal. When somebody tells you the rate of change of whatever it is proportional to something, you always have this little proportional sign. Okay, so the rate of change, that's dy dt, y is the amount, t is time. The rate of change dy dt is proportional to the amount present. Then we can say it is actually equal to a constant times that thing. And since this is decaying, we want dy dt to be negative, because when dy dt is negative, then our function is a decreasing function. Calc 1, baby, Calc 1. Okay, so dy dt is equal to negative ky. K is greater than 0. And K is our diffusivity constant. It tells how fast the stuff is going to decay. All right, the bigger K is, the faster the decay. All right, any questions about me setting up this problem yet? All right. So I am going to change this to y of 0 being y naught. So y of 0 is the initial time that we're looking at it, and that is the initial amount present. All right, so let's solve this differential equation. As you can see, the dependent variable is still y. The independent variable is now t. So I have dy is equal to negative k y dx. So dy over y is negative k, and that should be dt. Man, my brain. Okay. All right, so this is just right for a separation of variables solution. We're going to multiply, we're going to integrate. integrate dy over y, and integrate minus k dt. All right, so dy over y gives us the log. We don't need the absolute value because this is an amount of material, so y is always positive, is equal to negative k times t, we integrated negative k plus a constant. So I'm gonna do what I did before. In order for me to get the y, I'm going to raise it all to the e to that power. Okay, and so on the left-hand side, I get e to the log of y. Their inverse functions, I just get y. And on the right-hand side, I get e to the negative k times t and e to the c. And just like before, we want e to the c to be a constant. So we'll let e to the c be a constant and we'll call it a. So I get y is equal to a e to the negative k t. Okay, that is a general solution. To the radioactive decay problem. Now, if y at 0 is equal to y0, so if y, when x is 0, so y at 0 equals to y0, says when t is 0, then y is equal to y0. So I get y0, that's what goes in for y, is a e to the negative k times 0. Oh, that's just 0. And so I get y0 is equal to a. So now I know a is y0. So therefore y of t, in the place of a, I can put y0, the initial amount, e to the negative k t. So that tells me at any time t, the amount of substance that I have. At any time t, that tells me the amount of substance that I have. Okay. So I have two questions. The first one is, let's find the half-life. What in the world is half-life? All right, so find the half-life of the radioactive substance. So that says find the time t when 1/2 of the initial amount is left. Okay. All righty. So if 1/2, so we said, so we need y of t to equal 1/2 of the initial amount. So that's y0. So y of t has to equal y0. And then we need to solve for t. And that t will be our half-life. And I'm going to give it a name when we're done. Okay, so we get 1/2 of y0 is equal to y naught e to the negative kt. All right, we have y naught on both sides. Y naught is not 0 because if our population is 0, it'll never change. So we can divide by y naught and we get 1/2 is equal to e to the negative k times t. Now, how can I get that t? T is in the exponent right now. I need t to come down. So what can I do to this to make, for me to be able to get to the exponent?
Wait, did you say you want t to come down? So
Yep. There's a function I can apply to it that will give me the exponent. Guys, I hear crickets. All right, let's take the log of 1/2. That's going to give me the log of e to the negative kt. Anytime you got something in the exponent, take the log of it. All right, the log and e again are inverse functions. So I get the log of 1/2 is equal to negative kt. All right, so therefore t is the natural log of 1/2, and it's negative over k. And if you use log properties, you get the natural log of 2 over k. So that's going to be the half-life. So tau equal to the natural log of 2 over k is the half-life. That means at that time, half of the whatever it is that you had is now gone and you only have 1/2 of it left. Okay. All right, any questions about the half-life? All righty, let's go on to a meaty problem. All righty. Scientists who do carbon-14 dating, that's to determine how old something is, like bones. I think they just found the tooth of a mammoth, a woolly mammoth, something. And they obviously they can figure out, get an idea of how old it is by using carbon dating. So carbon dating is often used, scientists who do carbon dating often use a figure of 5,730 years for its half-life. So whatever it started, it will take that amount of time, that many years, before it has half the carbon in it that it started with. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. Okay. So we need to find the age of it using this. All right, so they give us the half-life. So given, the first thing is 1, the half-life. Tau is equal to 5,730. So that's the half-life. The other thing that's given is 10% of the nuclei present have decayed. Okay, so we already know our formula looks like y of t is equal to y naught times e to the negative k times t. So we know that. Okay. So first thing we can do is we can solve for k. So what do we know? We know tau is the natural log of 2 over k. So that implies that k is the natural log of 2 over tau. All right, so for our problem, k is going to equal the natural log of 2 divided by 5730. Okay, is really small. Okay, so this thing is decaying really, really small. K is approximately 1.2 times 10 to the minus 1, 2, 3, 4. So K is pretty tiny. All right. Okay. So if 10% of the nuclei have decayed, that means presently we have 90%. So presently, we have 90% still left. So we need to know what that T is. So Y of T is going to equal 90% of the original amount, but at the same time, Y of T is equal to Y naught E to the negative K T, and we already have K. So they must be equal. 0.9 Y naught is going to equal Y naught E to the negative K T, which is known. So we get 0.9 is equal to E to the negative K T. So once again, I need to get T out of the exponent. So I'm gonna take a natural logarithm. So the natural logarithm of 0.9 is equal to the natural logarithm of E to the negative KT. That brings that down. So I get the natural log of 0.9 is equal to negative K times T. So our time that it took for the 10% to decay is going to be the natural log of 0.9, and it's negative, divided by K. So let's see what we get. So we get T equals those are yours, minus the natural log of 0.9 divided by, and what was K? I'm just going to stick in K. Okay, we got 1 minute. Okay, 870 years. So almost 871 years. Okay. So 871 years. So that means that the sample is 871 years old. Okay, we will do one more problem like this on Monday. All right, I am having office hours today at 3, which will be in 15 minutes for those who are interested.
Have a good day.
All right, you have a great day.